Grade 12 learners, before you attempt to do this question paper, I will advise that you go to our full playlist of Momentum and Impulse. The lessons in those videos will assist you to solve any question paper that tests Momentum and Impulse with ease. We are going to look at question 4 of the November 2014 question paper. Before we can attempt any question in physics, we use a problem-solving strategy that is made up of 4 rules. The first rule that we are going to apply is the I rule. I stands for interpretation of the problem. This rule will assist us to visualize the problem and have a better understanding of the problem. In order for us to visualize this problem, we are going to draw a picture that represents the motion that is described, choose direction, and write down the given information. Without further ado, I'll read the question. Dancers have to learn many skills, including how to land correctly. A dancer of mass 50 kg limps into the air and lands feet first on the ground. She lands on the ground with a velocity of 5 meters per second. As she lands, she bends her knees and comes to a complete stop in 0.2 seconds. If one was to visualize this situation by drawing a diagram, it will look as follows. But before I draw this diagram, perhaps I can choose direction because I see I have vectors there. I was given velocities. So I'll say that take up as positive. Up is our positive direction. This would mean that any vector that is pointing in the upwards direction will be regarded as positive, and vice versa. Now, in this situation, we are saying that perhaps we have the ground and we have a dancer here. This dancer limps into the air. That means she sort of jumps into the air, and now she'll be in the air, and obviously because of gravity she'll come back down to the ground. Now as she does that, what happens is that she bends her knees as she comes down to the floor. This dancer, we're saying here that she has a mass of 50 kg, and we are saying that when she lands here, she will land with an initial velocity of 5 meters per second. Now I'm calling this an initial velocity because eventually she actually comes to a stop. That means she will have a final velocity. Remember that when she is landing here and she limps, she bends her knees here when she's landing. She is still in motion. That is to say that there will be some initial time here, ti, because at some point she will actually land and stand straight, where now the time will be 0, and at this point her final velocity would be 0 meters per second. She will completely stop at this stage. So what I'm saying is that while she is bending here, she is still in motion, and the time will be going on for a period of change in t is equals to 0.2 seconds, until she stands straight up after this 0.2 seconds, where now she's completely at rest. Now she has completely stopped. So definitely there's a change in momentum from here to when she stops. I hope that actually makes sense as I'm describing it. And that is all the information that we are given in this problem. Now that means we are done with interpreting our problem. The second rule that we're going to use to solve the problem would be problem classification, and is represented by the letter C here, to say C for problem classification. Under classification, what we actually do here is that we match this problem that we're given, question 4, with the part or the topics that would relate to this topic, would relate to this problem. When I look at this given information and the scenario that I have here, I think this relates very well with impulse and momentum. Perhaps also Newton's second law could also be used here, because I can see here that there's a change in momentum here. There's initial velocity, final velocity, and there'll be some form of change in momentum. So I could be asked around change in momentum, and they've given me time here. I could expect questions around impulse, or even Newton's second law, either in terms of momentum or MA, because now when you have the velocity and the time, you can somehow calculate the acceleration as well. Now that I'm done with classifying the problem, I'll actually go to the third rule, which we call the A rule. And this rule is problem answer. The A stands for answer. This means now we are going to answer our questions, because I believe that interpreting and classifying this problem, we have a better understanding of this problem. It should be easy for us to answer this problem. Now 4.1 says to us that we should calculate the momentum with which the dancer reaches the ground. If we look at our situation here that we have described, we are actually looking for the momentum when the dancer reaches the ground. It means we are looking for the initial momentum, because remember, the 5 meters per second is when this dancer reaches the ground. So that means here we are looking for P initial. And we know from the definition of momentum that momentum is equal to the product of the mass times the velocity. In this case, it will be Pi is equal to mvi, because it is the initial momentum, therefore it will depend on the initial velocity. This then becomes a situation where we then substitute the given information, which is the 50 times. Now, one thing that we also have to notice is that the velocity here is a negative 5 meters per second, because it's a vector that actually goes in the opposite direction to the direction that we have chosen. Remember, we are saying that any vector that goes up is positive, and if you look at the 5 meters per second, it's actually going down, so it should be a negative vector according to how I've chosen direction here. So this means here I'm going to substitute negative 5 meters per second. Now from here, this question becomes very, 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 very boring, because really we just use our calculator to find the answer. And in fact, even if you look at these numbers, they don't really need a calculator. You can do them with your head, because 50 times a 5 should give you a negative 250. Our final answer would therefore be the initial momentum to be given by 250 kilogram meters per second downwards. Remember that the fact that the momentum is negative would mean that it is actually going downwards. So our momentum here is going downwards. Our initial momentum is equals to negative 250. It's actually 250 kilogram meters per second. It's going downwards. It's a vector that is pointing downwards. Now this question will be marked for 3 marks, and what they really mark here is using the correct formula, the substitution, and writing your final answer. Remember, this is not the final answer. The final answer should be written in such a way that you have the symbol for momentum you also have the number and the SI unit and the direction, right? And in fact, what I'm doing now, I'm doing the fourth rule where we are navigating the answer, the end rule, what we call the end rule. Navigating the answer is to check if we've corrected the correct quantity, what we asked in the question, and also if our answer makes sense. So this answer makes sense because remember, velocity and momentum are directly proportional. That means if the velocity is going downwards, the momentum should also go downwards. And that number also looks reasonable because we're multiplying the 50, which is the mass of the person, by 5. We should get something like a bigger momentum, like 250. Now, if you look at this rule, it says I can solve any problem if I apply it. We then use the same rule to answer other problems. In other words, I go to the A rule again to answer the next problem. The next problem here, 4.2, says define the term impulse. Because all of us, we have went through the videos in my YouTube channel, we should know that the product of the net force and time during which the force is applied. During which the force is applied. Now this question is marked out of 2 marks. And because we were answering the question, we were doing the A rule. We are going to then now do the navigation, the end rule. The end rule basically for this type of a question is to check if there's no spelling errors here, if the sentence is well constructed. So here we're saying the product of the net force and the and time during which the force is applied. That looks good to me. It should guarantee me the 2 marks. Now we then go to the next question. In other words, in our rules, we go then to the A rule again. Question 4.3 then says to us that calculate the magnitude of the net force acting on the dancer as she lands. Remember that when the dancer lands here, the surface will exert to her a time-varying force until she stops there. There's going to be a time-varying force, meaning forces that change over time. And those forces, we average them into a single force that we call the net force. So in other words, the average of all these forces that I've thrown there will then give us one force that we'll call the net force. And we can see here as I'm drawing it that this very net force will actually be a vector that goes upwards because it is applied by the surface on the person. So this is the net force that we are required to actually calculate. To understand what I was talking about there, I will still encourage for those of you who haven't looked at our lessons to go there, because I explained and described that whole concept of time varying force. Now, to get this very force, I can use the fact that impulse is defined as the net force times the change in time. Basically, question 4.2 was a hint that we should use it here to answer 4.3. But also we know that the impulse is the same as the change in momentum from the impulse momentum theorem. So this means here I can say then that the impulse is also the same as the change in momentum. Now my focus will be on this part of the equation because I'm looking for the force, I have the time, and the change in momentum can also be built in there. In other words, this would imply that I can write this as the net force times time is equals to the mass final velocity minus initial velocity. Remember, this is the change in momentum. Then I have everything here. I can then substitute. This would mean now I'll have the net force times 0.2, because that was the time it takes for the person to completely land here. And we're saying that this is equals to 50 kg. And then the final velocity, remember, is 0 because this person comes to a complete stop. And she landed there with -5 meters per second. Remember, it's a negative because we chose up as positive, so meaning a vector that goes down would be negative. Because here we have -5 as the initial velocity, it means we're going to have a +5, because remember here, the negative and the -5 will give me a positive. At this stage, this problem becomes very, 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 very boring. Because what we're going to do here is that we're going to divide both sides by 0.2 so that the 0.2 cancels and I'm only left with the net force this side. And here I have a 50, 0 plus 5 over 0.2. And I can simply punch that in my calculator to say 50 times 0 plus 5 close bracket over 0.2. And this gives me a force of 1,250 newtons. Now, when we look at this force is positive, right now I'm done answering my question. I'm navigating my answer now to see if the answer makes sense. So the first thing is that you check if you calculated the correct thing, the correct quantity, which it is because it's the net force. But also when we look at this number, is quite a big number, of course, because we have a very small time, 0.2, to land on the surface, so expect a bigger force. Remember that the time and the force are inversely proportional. If you have a small time, you'll expect a bigger force. The other thing is that this answer is actually positive, meaning that it's a force that is going upwards, and that makes sense. We expected this force to actually go upwards. So our force here, we expected this force to go upwards to be the 1,250 Newton, because it's a force that is exerted by the surface on the person. It is experienced by the person. The surface pushes this person upwards. It sort of stops the momentum or changes the momentum of this person as they are coming with a momentum of 5 times the momentum of 250. Really, it's stopping that momentum, the surface, hence the force is going upwards. Now, after you are done with navigation to see that your answer makes sense, you can really move on to the next question. So here we are going to be marked out of 3 marks. So that means they'll mark using the correct formula. Either you start from any of these equations, they'll give you the mark, and they'll also mark you for the correct substitution, the fact that you have put the correct values there, and the last mark will actually come from a final answer. You have to notice that here I didn't write the direction to say upwards. The reason being is because the question says calculate the magnitude. They're actually asking us to get the magnitude of the net force. So that means we only write the number without the direction. That's what the question is asking us. Very important to not do that mistake of putting direction if they didn't ask you for the direction. Now, I can see here that before we do 4.4 and 4.5, we are given more information here. That means on our rules, the problem-solving strategy that we are using here, we actually going to start back on interpretation, because if they give us more information, it means they are sort of changing the situation. So obviously, our interpretation would also add on or change completely. So let's see what they say here. They say that assume that the dancer performs the same jump. So the dancer performs the same jump as before, but lands without bending her knees. Very interesting. So just for me to redraw this diagram, I will then say that we still have the surface here, and the dancer will limp again and go into the air so that they perform the same jump. Now, the difference is that when they land on the surface, they actually don't bend at this stage. They just land completely and then they come to an instant stop. You have to understand that now, because she's not bending, there's no additional motion as we had here. There's no bending and unbending to stop. She comes to an instant stop. And you can imagine that when this happens, she'll probably injure herself. She might hurt her knees or her back because she's just landing instantly. Now, this means that during this land, we'll still have an initial velocity of 5 meters per second. So -5, because remember we said it's the same motion. We said that they jump in the same way. They jump as before, so meaning our momentum will be the same, and of course, the final velocity will be 0. The only difference now here is that this dancer will take a very short time to stop. If we look at the changing time here to stop, will be much smaller compared to the first situation, because there is no additional bending of knees here. So the time will be much smaller than this one when they land without bending their knees. Now, I think that's what is happening in this situation. We can go now into the second rule, because that was interpretation, classification. Well, I'll still say this is a problem that will require impulse, changing momentum. It's just that maybe now things will change. Maybe they might say we should calculate the time because we can see that the time is smaller now and stuff like that. So we can go answer the problem now after classifying this problem. To answer this, I'll read 4.4 that says, will the force now be greater than, smaller than, or equal to the force calculated in 4.2? So they're asking us a problem where they require us to compare the answer that we got here for the force with this new situation to say, will this force be greater than, smaller than, or equal to? This type of a problem is part of navigation. It actually assists us to assess our answer in 4.2 to see if it makes sense. So what I mean is that if we compare this situation here with the first situation here, there is certain expectations that we need to have in terms of the force that they're asking us. And what actually they've done here is that they've changed a variable in our equation, the time. The time is now smaller, and we want to see that if the time is smaller, what is the net force? How does the net force change? So is another way of navigating a problem. Now, here we can see that because the time is small, the net force should actually be bigger. Now, what I mean by this is that you must remember from Newton's second law. If we look at N2, Newton's second law, we said that the net force is inversely proportional to the time. That means that when the time gets smaller, the force should actually be bigger. And that's what's happening here, because now if this person doesn't bend their knees, they'll spend a short time to stop. That means now we are going to experience a much bigger force here compared to the force that we had when the time was bigger, because you're saying this time would be smaller than the first scenario. So expect the force to actually increase to be much more bigger because the time is smaller. In fact, another way of solving this previous problem here is to actually use Newton's second law to say the net force is equal to the change in momentum over the change in t, where now you're going to have mv final minus mv initial over change in t. And this, if you are paying attention, you would see that it looks exactly like this, because you'll substitute the 50, the 0, the 5, and the 0.2. You can try this and see if you get the same answer. Now we are saying here that the time is small, the force should be bigger. So to answer this problem, we'll choose the option of a greater than. Our force should be greater than the force that we got in 4.3. So here we'll write greater than. Now question 4.5. So basically, this problem on its own is navigation of that answer. We expect the first to be greater than. So we expect the first that will be greater than this one. Now I'll go to answer question 4.5, which says give a reason for your answer to question 4.4. I mean, to answer this question becomes really boring because already we have answered, we've given reasons when we were interpreting this problem to say why is it greater than, right? So perhaps maybe here what we need to do is to put it in words. Remember that we said the jump is the same. In other words, the momentum here, the change in momentum here hasn't changed. It's still the same as the change in momentum in the first scenario. Is the same change in momentum as here because we still have the initial velocity of that and final velocity of 0 as well. So the change in momentum here also will be the same as the one in this problem here. So this means the only thing that has changed is actually the time is smaller. Now I'm going to put all that together to say since the change in momentum is the same and the time it takes for the dancer to land, or rather maybe to say to stop, is smaller. Then the net force exerted by the ground on the dancer must be greater, right? So we're saying here that the change in momentum is the same, but the time is small. Therefore, the net force should be greater. This net force should be greater. It's exactly what we explained here. That's how you'll answer that question. These two questions will come out for 1 mark because here you just, write greater than. And here they will mark the fact that you acknowledge that the change in momentum hasn't changed, right? It's still constant. It's the same as the previous change in momentum. This is to say you understand that the jump is still the same. But also what has changed here is the time. So the time has changed to give you a mark for that, and therefore the final and therefore the net force should actually be greater. They'll give you another mark for then saying the net force should be greater. And obviously, always when we do proportional equations where we look at how each quantity changes and how it affects the other one, the other quantity should be constant. In other words, when this and this change, the change in momentum should be constant. If the change in momentum were to vary and the net force to vary as well, the time should be constant. That's how we use these equations. Now, to navigate this answer, you can check if there's any spelling errors on the answer that we wrote and if the grammar is correct. And if you're satisfied with the answer, then it is correct. So that is to say here that you do your navigation after answering any question. We call this I can rule academic constitution, meaning these are the rules that you must follow when you solve physical sciences problems.